with water. And water, we'll have a couple of lectures on water. Then we're going to follow up with nutrients. And then metabolism. And then after metabolism, I don't remember what the next one is. Anyway, so we're starting at chapter 2. And we're going to repeat some things that you've already had. You probably have already had diffusion and osmosis. You know what xylem and phloem is. And I'm not going to go over these objectives. These are the basic learning objectives that we're going to be talking about. And we're going to go right into the deep end, because what we're going to be talking about now is physics. And anybody here tell me what these things are symbols for? These little squiggly lines? Anybody know? I bet you know. Do what? Nope. It does. It has to, but what are those? Where do you find those symbols mostly? Nope. What? What kind of graph? It's an electrical measurement to resistance. So if you're building a circuit board, wherever there's a resistor, you have one of these squiggly lines. So now you can go, okay, yeah, I remember now. You know, totally outside of life processes. We're talking about resistance. And we're using this case is places where water or air movement are affected, or there's a bottleneck. Resistance to flow. Remember, CO2 has to go in, CO2 and oxygen goes in, water has to come out of the vacuole, not the vacuoles, I'm so out, stomates. And so above the leaf, if there's no wind blowing, then you have this thing called the boundary layer, which is just this layer of air right above the leaf, and it very quickly runs out of CO2. The air's not moving, a little bit of CO2 goes into the leaf. There's a scientist on campus named Heilman in soil crop science, and I don't know if he does this now, but he used to be concerned with the first 1/10 of a millimeter above the leaf. That's where he did all his research, because yield is limited due to the resistance of air movement. So the faster the wind blows, the more fresh air you get, and also the faster the wind blows, more water comes out of the stomates. So if you're in a well-watered, ideally the best environment is well-watered soil with some wind. Because remember, minerals can only move up with the water. So if there's no loss of water through the stomates, there's no movement of minerals or limited movement of minerals in the plant. Okay? So we have these different areas. You all know what a leaf looks like. We usually find stomates on one side. And here we have the cuticle, and here we have the cuticle again, and this is basically wax. So the leaf is waterproof, except for the stomates. So that's where things can move in and out. Eventually, we're going to put a lot of this together when we talk about transport. Here is the vein. So once the CO2 enters and is absorbed into these leaf cells. It'll eventually find its way into sucrose and move in through the veins. Water will also come out of the xylem and eventually work its way through the stomates. Now, transpiration. Plants lose 95% of their water by transpiration. Transpiration is defined as loss of water as vapor. And the other part of the leaves are protected by this waxy layer, a cuticle, different kind of waxes. A lot of people, there are people that research, and you can put a piece of tape usually on the leaf, a piece of good Scotch tape, and you can pull up the cuticle and then where the stomates are. And so then you can put that on a microscope slide and you can actually study the cuticle and the distribution of stomates fairly easily. You know, it's a little trick you can use. Water is lost by evaporation. It escapes through the stomata or stomates. There can also be lenticels that are around. And later on we're going to talk about how the hole, the stomate, is regulated, the size of the stomate, how open or closed it is by the guard cells. Now, once again, same thing. Here we see the hole is the stomate, and these two cells here are the guard cells. So the driving force for how water moves out is the area inside the leaf, right below the stoma, and the condition of the air right outside the leaf, the boundary layer, and then, of course, the wind, this kind of stuff. So we describe this in terms of, usually in terms of resistance. What controls transpiration? Humidity, temperature, of course. Humidity, how much water is already in the air. Temperature, more water, the higher the temperature, the faster the water is going to move around a bit. And of course the wind speed. And like I said, the boundary layer is one of the main resistant points to flow. And just think about that. And this is not just in the lab. This is right outside right now. I don't know if the wind's blowing or not, but if the air doesn't mix in that half a millimeter or a millimeter above the leaf or below the leaf, wherever the stomates are, then there's no way for the water vapor to come out or for CO2 to go in. We're talking about water now, but of course, at the same time as water moves out, CO2 moves in. And here again is what we started with. So we have these resistance circuits, okay? And here we have movement this way, so resistance in the cell. And then here we have these areas that can be assigned values that are similar to what a resistor would have. You know, a resistor regulates the flow of electricity. So we use the exact same squiggly lines to assign values that regulates the flow of water and our CO2. Okay? Questions about that? Yes, sir.
When water leaves the vein as it's coming up the xylem and into the leaf and then disperses through the leaf into, you know, the mesophyll to eventually go out the stoma, does it go through mostly the plasma desmata, or does it do a lot of like apoplastic?
Okay, the question is, how does water basically move into the leaf and then into the open spaces? And you said, is it plasmodesmata or is it through open spaces? It's everything.
Okay.
and when we talk about roots, we'll talk about movement of water in the cell walls, and then movement of water into the cells. So the water moves through the cells, and also the water will move through the cell wall material. Okay, remember, with the xylem, you're talking about a dead open pipe. And what is amazing, that is under normal conditions, water moves, and we'll talk about this today, but let me go ahead and talk about it. Water moves as a continuous stream from the bottom, the very tip of the bottom of the plant root, to the intercellular space. And in fact, if we disrupt that column, that continuous column of water, the plant's in trouble. And we'll talk about that next time, I think. Okay, so what we talk about now, next term, is something called psi, and we're going to have psi sub W, which is water potential and pressure potential and osmotic potential. And again, these are just the general things that we've been talking about. And here is the value of psi in megapascals. At 100%, the value of psi is 0. So the highest, pure water has a potential of 0. Okay? And I know that's just confusing as hell. Anytime you put something in water, you lower the concentration of water, you lower the potential. Okay? So pure water is 0. Plants are, let's say, -5, -10, whatever. And here you're seeing the relative humidity. You're seeing what the water potential is in megapascals. So at 20% relative humidity, we've got 217, -217. So it's always negative. Here we can see the leaf and the atmosphere. Here is the temperature. Here's the temperature. And if we look at these values, you can see that we can see the leaf versus air. And don't worry about, you don't need to know these, of course. But you'll notice in these different conditions how we have this difference between the inside and the outside. Okay? And again, there are people that their research centers on just air movement or water movement or CO2 movement in and out of the leaf. That's it. And we can actually put a resistor on a leaf, and we can actually measure the resistance to flow. You know, it's not really electrical resistance, but we can actually measure that resistance to flow. Pretty sophisticated equipment. Okay? So the more wind we have, the more movement and the more loss of water from the leaf. And this shows you the boundary layer thickness with wind speed, okay? So at wind speed 0.2 meters per second, you have a fairly good boundary layer. If we get up to 1 or so, and this is just a break in the graph, it's lowered a lot. And then if we get up to 7, 8 miles, then the boundary layer is almost non-existent because the wind blows. The air that is immediately above the leaf is replaced with new air. Okay? And I know I may be going over this again and again, but it's pretty important. Okay? Okay, I'm finishing right now. I will pick this up Friday.